For this video, we're going to be looking at some real-life examples of exponential growth and decay functions. Number one says the value of a car Y in thousands of dollars can be approximated by the model Y is equal to 25 times 0.85 raised to the t, where t is the number of years since the car was new. First, I want to tell whether the model represents exponential growth or exponential decay. Well, I know for exponential growth, my b value needs to be greater than 1, and for exponential decay, my b value is between 0 and 1. So looking at my model here, I see that my a value is 25, and my b value is 0.85. And 0.85 is between 0 and 1. So since it's between 0 and 1, this one is going to be exponential decay. Okay, next I want to identify the annual percent increase or decrease in the value of the car. Well, here, because t is given in years, the decay factor is going to come from that 0.85. And so I know that 0.85 is equal to 1 minus r, because my b value is equal to 1 minus r. And I can actually rearrange this equation to be that r is equal to 1 minus 0.85. And when I do 1 minus 0.85, I get that r is equal to 0.15. So that means that the annual percent decrease, since this is a decay, it's asking for the percent, so I need to move this decimal place 2 to the right, so it's going to be 15%. Okay, and then the last question says to estimate when the value of the car will be 8,000. And so looking at my variables, t is for years, so that means that y is for the amount, the value of the car. So I'm looking to see when this function is equal to 8, since y is in thousands of dollars. So I'm looking to see when 8 is equal to 25 times 0.85 raised to the t. So to do that, we're going to go over to Desmos and type in this function. So going here, I want to go ahead and add a table. And I'm going to replace this y1 with my function. And that is 25 parentheses 0.85. I'm going to hit this A to the B button and put X, and then you need to put underscore 1. Which is right here. Okay, so we have our table. And now I'm going to put in numbers to see when my y value ends up being close to that 8,000. So I put in 1, I get 21.25, so not that one. 2, 3, 4, 5, 6, 7. So I see at 7, my y value is approximately 8. And so that means this is going to be after 7 years. Let's look at this next one. The population P in thousands of Austin, Texas during a recent decade can be approximated by y is equal to 494.29 times 1.03 raised to the t, where t is the number of years since the beginning of the decade. First, I want to tell whether the model represents exponential growth or exponential decay. So I need to look at my b value for that. So my b is going to be this 1.03. And I see that is greater than 1. And since it's greater than 1, this is going to be exponential growth. Next, it says to identify the annual percent increase or decrease in the population. Well, I know this one's an increase since it's growth. And I know that b, which is 1.03, is equal to 1 plus r, since this is an exponential growth. And so solving for r, I just subtract 1 from both sides, and I get that 0.03 is equal to r. And this one's asking for percent, so I need to make sure I need to change this decimal to percent. So it's going to be 3%. So this is an annual percent increase of 3%. Okay, now it says to estimate when the population was about 590,000. So this one again, it's looking at our function is in terms of thousands. And so that means I'm looking to see when y is equal to 590. So I'm looking to see when 590 is equal to 494.29 times 1.03 raised to the t. So going back over here, I'm going to just change my function. So this is now 494.29 and 1.03 in here. And I'm looking to see when this is at about 590. And I see that that is going to be at year 6. Okay, 3 and 4 are a little bit different. This time we're going to actually have to write our own function. So number 3 says, in 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by 1.18% each year. First, I want to write an exponential growth model using the population y in billions, t years after 2000. Well, we know with exponential growth that my function is going to be y is equal to a times 1 plus r raised to the t. So I need to know what my a is and what my r is. My a, again, is just my starting value. And here I see that I'm starting at 6.09 billion. So a is equal to 6.09. My r is the rate that's increasing by. And I see that's by 1.18%. However, remember that our rate is actually supposed to be written as a decimal, not as a percent. So that means I need to move that decimal place 2 back to get that r is equal to 0.0118. So that means when I'm writing my function, again, this is y is equal to a times 1 plus r raised to the t. So I get y is equal to 6.09 times 1 plus 0.0118 raised to the t. And so to find that out, I get 6.09 times 1.0118 raised to the t. Okay, part B says to estimate the world population in 2005. So I'm looking to see how many years have passed. Well, this is starting at the year 2000. So in 2005, that means 5 years have passed. So t is equal to 5. So plugging that in for t, I have y is equal to 6.09, 1.0118 raised to the 5th power. And so I can use Desmos for that again. So do 6.09 parentheses 1.0118, close parentheses, raised to the fifth power. And rounding that to the nearest hundredth, I get that y is approximately 6.46 billion. Okay, and then C says to estimate the year when the world population was 7 billion. So you could go ahead and plug in numbers into this equation, or we can use our chart again. I'm going to go ahead and use the chart. So I'm going to replace this with our new function. So that is 6.09 and then 1.0118. And I see to get to 7 billion, let's see what we get. It was approximately 12 years. And so 12 years past 2000, that's going to be the year 2012. Okay, let's look at one more. You take a 325 milligram dosage of ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by about 29% each hour. Write an exponential decay model giving the amount y in milligrams of ibuprofen in your system t hours after the initial dose. So again, I need to know what my starting value A is and what my rate is. Here I see that I start with 325 milligrams, so A is 325. And then it says it's decreasing by 29% each hour. So my R is 29%. But again, I need to rewrite that as a decimal, and so that's going to be 0.29. Here I have an exponential decay, so it's going to be 1 minus r raised to the t. My A is 325. My R is 0.29. So this is going to become y is equal to 325 to the 0.71 raised to the t. Okay, and then part B says to estimate how long it takes for you to have 100 milligrams of ibuprofen in your bloodstream. And so this time I want to see when y is equal to 100. So I have 100 is equal to 325, 0.71 raised to the t. So coming back to Desmos, I need to rewrite this function. So I have 325 0.71 and I see that it's going to take probably somewhere around 3.5 hours to have 100 milligrams. Since 100 is somewhere between 3 and 4.